Signals and systems, orthogonal signals, series on signals and systems, lecture number 1.11. The concept of orthogonality, it is imported into signals from vector algebra. There, two vectors are said to be orthogonal if they are perpendicular to each other. Concept-wise, it is from vectors into signals, but definition of orthogonality in signals is different from the definition of orthogonality in vectors. In the present session, the focus is on orthogonality in signals and its importance in expanding a signal, time domain signal, into frequency domain signal to see its frequency components. We also discuss briefly about sets, closed sets, and also about Gram-Schmidt procedure. Now, let us move into the core of the session. To begin with, we consider the definition of signal. Signal is a waveform or a function with one or more variables which is capable of conveying information on the nature of a physical phenomena. The key point to be kept in mind is it is a waveform. Signal is a waveform and it is capable of conveying information. These are two key words pertaining to definition of signal. If the waveform is of current or voltage or field, then it is called electrical signal. Signals can be divided into mechanical and electrical. Sound is an example for mechanical signal. And if the signal is in the form of current, voltage or field, then it is electrical signal. An example, practical example to electrical signal is output current or output voltage of a microphone. Microphone converts sound, which is mechanical signal, into electrical form, into voltage. So in the functioning of microphone, we have both mechanical signal as well as electrical signal. Some more points regarding signal definition. When the signal depends upon a single variable, then it is called one-dimensional signal. Speech is an example. Speech is a kind of sound. If the function depends upon two or more variables, then the signal is said to be multi-dimensional. Static pictures are examples for two-dimensional signals. They depend upon positions, horizontal position and vertical position. Hence, they are two-dimensional. Motion pictures are examples for three-dimensional signals. They depend upon horizontal and vertical positions and also on time. So, three-dimensional signals. Temperature, wind speed, air pressure. These are four-dimensional signals because they depend upon position. Position requires three dimensions and time, so fourth dimension. These are examples for four-dimensional signals. The classification is there, standard classification. According to this classification, signals can be divided into CT and DT signals. CT stands for continuous time, DT stands for discrete time. Another classification is into analog and digital. Analog is a kind of CT Digital is a kind of DT. One can say analog is subset of CT. Digital is a subset of DT. Causal and non-causal. This is another classification. Causal means which is 0 for negative values of time. Non-causal is one which is not causal. Real valued, complex valued, another classification. If the signal is real valued, then it is real signal. If it is complex valued, then it is complex signal. Deterministic and random signals. This is another classification. If the amplitude of the signal or magnitude of the signal is clear, it is mentioned without any ambiguity, then it is deterministic. If it can be specified only probabilistically, then it is random. Even and odd, this is another classification. Periodic and non-periodic. If repetition is there, then it is periodic. If repetition is not there, then it is non-periodic. Another classification is energy and power signals. If the energy of the signal is finite, then it is energy signal. If the power is finite, then it is power signal. A discussion about the classification that is shown or classifications that are given here. It is given in some other session because it is necessary to mention the classification here. It is mentioned briefly. Now we move to another classification which is not mentioned here. That is orthogonal signals and non-orthogonal signals. To understand that particular concept, orthogonal and non-orthogonal signals, we need to know something about orthogonality. Orthogonal signals. Two signals, f1 of t and f2 of t, they are said to be orthogonal over an interval t1, t2 only if integral t1 to t2, f1 of t, f2 of t, dt must be 0. This is the defining relation when f1 and f2 are real. If they are complex, then the defining mathematical relation is given here. Integral t1 to t2, f1 conjugate of t, f2 of t dt must be 0, or integral t1 to t2, f1 of t, f2 conjugate of t dt must be 0. So first one is for real signals, second one is for complex signals. One point to be kept in mind is orthogonality is defined with respect to two signals, like orthogonal vectors. Two vectors are said to be orthogonal. A single vector cannot be orthogonal. Orthogonality is with respect to orthogonality of a vector is with respect to another vector. In the same way, orthogonality of a signal is with respect to another signal. Some more information regarding orthogonal signal. In this slide, some examples are given for orthogonal signals. Trigonometric functions like sine n omega naught t, sine m omega naught t over any interval t naught to t naught plus 2 pi by omega naught for integer values of n and m. Similarly, sine n omega naught t, cos m omega naught t, and also cos n omega naught t, cos m omega naught t. These are all mutually orthogonal. Another example, exponential functions like e power j n omega naught t with n equal to 0, plus or minus 1, plus or minus 2, etc. These are all orthogonal over the interval t0 to 2, t0 plus 2 pi by omega naught for any value of t0. Another example set is given in 3 legendary polynomials. Jacobi polynomials are also examples for orthogonal functions. Now, orthonormal signal. What is orthonormal signal? Two orthogonal signals f1 and f2 are said to be orthonormal over the interval t1 to t2 if and only if integral t1 to t2 magnitude f1 square dt, it must be 1. Integral over f2 square also must be 1. Then only f1 and f2 are called orthonormal. So two orthogonal signals, they become orthonormal only if they satisfy this integral relation. Examples are 1 by root t, square root of 2 by t, cos 2 pi nt by t, n not equal to 0, and square root of 2 by t, sine 2 pi nt by t. These are examples for orthonormal. Now set, closed set. A set of mutually orthogonal functions g1, g2, g3, etc. gr, all are functions of time over an interval t1 to t2. This set is a set of mutually orthogonal functions. This set is called closed or complete set if and only if there exists no function x of t satisfying the relation integral t1 to t2 x of t gk of t dt equal to 0. So no function x of t should be there satisfying the relation. Integral x of t gk of t dt is 0. For k equal to 1, 2, 3, etc. r. It is possible to approximate an arbitrary function f of t over the interval t1 to t2 by a linear combination of set of n functions g1, g2, g3, gn, which are orthogonal over the interval. If the set is complete, approximation becomes equal. So after having the definition of closed set, in the second para, the importance, the utility of a closed set is being given, explained. It is possible to approximate or to expand approximately. It is possible to expand an arbitrary function f of t over the interval by a linear combination of a set of functions g1, g2, g3, etc., which are a closed set. If the set is complete or closed, then approximation becomes equal. If the set is not complete, it implies it is just approximation. So, mathematical implication is f of t can be expressed as sigma 1 to n cr gr of t. Gr of t is set. It may be closed or complete set or incomplete set. If it is complete, equality sign holds good. If it is not complete, then approximately equal. Here one can recollect by looking at this relation, mathematical relation, one can recollect Fourier series expansion. It has come, Fourier series expansion, it has come from this particular relation. For best approximation, which minimizes the mean of the square error over the interval, the quotients are CR. becomes equal to integral f of t gr of t dt by integral gr square of t dt. Here integration is from t1 to t2, both in numerator as well as denominator. The denominator can be replaced by kr. If the set g1 to gr of t is orthonormal, then kr becomes 1. Now we spend some time on Gram-Schmidt procedure. What is this procedure? This is about finding an expansion for signals. Expansion in orthogonal functions of a complete set. This procedure is able to construct an orthogonal complete set for the purpose of allowing valid expansion of a finite number of functions. A finite number of functions are there, and we want to expand them in terms of orthogonal functions. How to have those orthogonal functions? Gram-Schmidt procedure. It gives a methodology, a sequence of steps by which one can construct an orthogonal complete set that is useful to expand these functions. In such cases, the orthogonal set itself has only a finite number of functions. Let S1, S2, S3, Sn, all are functions of t, are the time functions to be expanded, and let u1, u2, u3, un, all are functions of t, time, are orthonormal functions. Then according to Gram-Schmidt procedure, S1 can be written as S11 u1 of t. S2 of t can be expressed as sum of two functions. One is S21 u1 of t, second one is S22 u2 of t. S3, it consists of three terms. First one is S31 u1, second one is S32 u2, third one is S33 u3. Like that, nth signal Sn, it consists of n terms. First term is Sn1 u1, last term is Snn un of t. This is the expansion. Now, things that are known, available in this expansion are, we know S1, we know S2, we know S3, we know Sn. Unknown, S11 is unknown, U1 is also unknown, S21 is unknown, U1 is also unknown. Like that, right hand side, several unknown things are there. How to find them? Procedure is like this. S11, one can find S11 using this relation, integration over one time period S1 square, this entire integration under square root. Once S11 is known, U1 can be determined from S1 by S11. So S11 is obtained from S1, U1 is obtained from S1, S11. Similarly, S21, integration over time period T, S2 of T, U1 of T dt. Using this integration, S21 can be obtained. S22 then is integration over time period T, S2 of T minus S21 U1 of T whole square dt under square root. S22 obtained can be obtained in this manner using this relation. And then U2 is equal to 1 by S22. S2 S2 of t minus S21 U1 of t. In a similar manner, S31, S32, S33, U3 can be obtained. The procedure, it continues. Same procedure can be adopted to find unknown quantities in the expansion for S4, S5, S6, etc. Once we know S11, S21, S22, etc., etc., and U1, U2, U3, etc., everything that is required to expand the functions, they become available to us, and expansion can be done without any problem. In case of n equal to 2, to find more general orthonormal functions, u1 and u2, let u1 prime is n1 u1 of t plus alpha u2 of t, and u2 prime is n2 u1 of t plus beta u2 of t. Select alpha and beta to satisfy 1 plus alpha beta is 0. Adjust n1 and n2 to normalize u1 and u2. These are some of the things which I want to share with you in this session. Before closing, let us recollect important areas that are touched upon in the present video. We started the session with a definition and explanation of signals. Then we moved on to orthogonality. From orthogonality, we moved to closed set concept. From closed set concept to their utility in expanding functions in terms of orthogonal function set. The session is concluded with a small introduction to Graham-Schmidt procedure. Hope this session is useful to you. We meet soon in another session with a new topic.